Welcome back. In this lecture, we will be discussing the Cuk converter. We have already discussed buck converter, we have discussed boost converter, and also we have discussed buck boost converter. Now, Cuk converter is the next in that series of DC-DC converters, and the difference between these three converters which we have discussed already and the Cuk converter is that the Cuk converter is a fourth order converter, which means it has 4 storage elements. The earlier, all the circuits earlier, all the other, that is the buck converter, the boost and the buck boost converter had 2 storage elements, one inductor and one capacitor, which were acting as the filters. So, they were second order converters. Now, Cuk converter has 2 inductors and 2 capacitors, thereby there are 4 storage elements, thus the order of the converter is 4, is the fourth order converter. The first fourth order converter we are going to discuss in this series of lectures on DC-DC converters. So, the lecture outcome is something like this. You will be able to describe the working of the Cuk converter and also you will be able to derive its voltage gain. Then you will be able to explain the shape of the relevant waveforms and you will be able to design a Cuk converter based on the user specifications or requirements. Okay. So, let us get started. Though the circuit diagram of Cuk converter is as shown, you can see there are 2 inductors L1 and L2 and 2 capacitors C1 and C2, thus there are 4 storage elements. That is why it is called a fourth order converter. Now, the input is connected in series with L1, C1, L2 and C2, where C2 acts as the filter capacitor and the load resistor is connected in parallel with C2. Okay. So, in the series path between the source and the load, you have L1, C1 and L2. C2 is in parallel with the output. Switch is connected between L1 and C1 and diode is connected between L2 and C2. When the switch is closed, the diode will be open and vice versa. So, at a time either switch or the diode will be open, both of them will never be open, and since we are doing the continuous conduction mode of analysis, both of them will never be open as well. Okay. So, when switch is closed, diode will be open, and when switch is open, diode will be closed. This assumption is based on the fact that the circuit is operating in continuous conduction mode, that is, the current through the inductor L1 and through the inductor L2 are continuous. They are continuous currents. These inductors are large enough so that IL1 and IL2 are continuous. Okay. Now, if you observe the polarity of the waveforms, observe polarity of the voltages across these passive elements, you can see for an inductor L1, VL1 is taken with positive on this side, left side, and now capacitor, the positive plate is the plate on the left side, current through it is from left to right, IC1. Similarly, for inductor L2, the current is from right to left, you can see the direction of current is from right to left, IL2, and the voltage polarity is from left to right, positive is towards the left and negative towards the right. So, this is the way VL2 is polarity is marked, and this is the way VL1 polarity is marked. Similarly, VC2 is also marked like this. Okay. Now, output voltage polarity, top side is positive and bottom side is negative. While we do the analysis, it will be clear to you that even for a Cuk converter, the output has a polarity reversal. That means similar to a buck boost converter, a Cuk converter also has a polarity reversal at its output. The advantage of Cuk converter is that now you have an inductor in series with a source, which means this inductor acts as a filter to filter out the harmonics in the input source current. So, we have an input filter as well as an output filter. In earlier circuits, we did not have an input filter. So, this one will serve as an input filter. Now, let us try to derive the voltage gain of this Cuk converter. Now, if you list down the salient features of a Cuk converter, as I said earlier, it is a fourth order converter. There are 4 storage elements L1, L2, C1 and C2. So, there are 4 storage elements and hence the name fourth order converter. Similarly, unlike other topologies which you have seen earlier, the capacitor takes part in power transfer along with inductors. Earlier cases, that is the buck boost and buck boost, it was only the inductors which were taking part in power transfer, and the capacitor was only acting as a filter. Here one of the capacitors will takes part in power transfer. Precisely C1 will take part in power transfer as well, along with the inductors L1 and L2. C2 the role is same, it acts as a output filter only, filter capacitance for reducing the voltage ripple. Now L1, which is connected in series with the source, acts as an input current filter. Okay. Then the output has a polarity reversal, which is similar to a buck boost converter, which means the gain will have a negative terminal. The gain will be minus D by 1 minus D, exactly same as a buck boost converter with the reversal of polarity. Output voltage may be higher or lower than the input voltage, that is already discussed in buck boost converter. When D is less than 0.5, the output voltage will be less than input voltage, and when D is more than 0.5, output voltage will be more than input voltage. When D is equal to 0.5, your output voltage will be equal to input voltage with a negative polarity. Okay. So you will be, this is a versatile converter, you can get a voltage less than, equal to or more than the output voltage. Only flip side is that it will have a polarity reversal, but the advantage is that you have an input current filter. Okay. And this is a fourth order converter. Since there are two more storage elements, the calculations become little more involved. So the assumptions is that both the inductors are large and the current through them are constant, currents in them are constant. This is a assumption which we will revisit later and find that the currents are not constant, it definitely has some ripple. Okay, but still they are large enough so that the current is continuous. Okay, and both capacitors are large, the output voltage across them is constant. That is, this voltage Vc2 as well as V0 is constant. Very shortly we will see it is not constant, they have ripple in output voltage as well as Vc1, we will see that. To make analysis easier, we make these assumptions, and immediately after deriving the voltage gain, we will revisit these assumptions and we will see that these assumptions are not valid, and definitely they have some current ripple in the inductors and some voltage ripple in the capacitor, but still these assumptions makes the analysis easy. Now the circuit is operating in steady state, that is, whenever a change in input happens, the circuit undergoes a transient, and once the transients die out, what is remaining is the steady state. Now in this analysis we are assuming that the circuit is operating in steady state, the transients has died out and the circuit is operating in steady state. So the waveforms are all periodic. So that is third assumption. Then the assumption is that the switching period is Ts and the switch is closed for a time dTs, where D is the duty ratio of the switch, and for the balance time, which is 1 minus D into Ts, the switch is open. Switching frequency is 1 by Ts and the components are ideal. With these assumptions, which are similar to the assumptions we made for the previous three converters, let us start analyzing the Cuk converter. Now one important difference here is that earlier we were using volt-second balance across the inductor. This was based on the principle that the average inductor voltage must be 0. We are not going to use this one for Cuk converter analysis. Instead, since we will be using Ampere-second balance on capacitor C1. This will be used to derive the voltage gain of the Cuk converter. Okay, that is the average current through C1. That is true even for C2, but we will be using the average current through C1 will be 0. That is, if the circuit is operating in steady state, the net average current through the C1 should be 0. Using that formula, using that as principle, we will be deriving the voltage gain of the Cuk converter. Okay. So what I am trying to say is that the net average IC1 must be 0 if the circuit is operating in steady state. So let us write the Kirchhoff's mesh law on the outer loop. This is outer loop. Okay. Let us write the Kirchhoff's voltage law. Let the current flow be like this. Now let us do this. It is Vn minus, see the polarity of the voltage, it is minus VL1 minus I am sorry, this is Vc1, I am really sorry for this mistake. This is Vc1 minus VL2 minus V0 is equal to 0. Now, the Kirchhoff's voltage law has been, mesh law has been written for the outer loop, the loop where S and D is not a part. Input inductor 1, capacitor 1, inductor 2, capacitor 2. So, this outer loop. Now, what happens is that, what is the average voltage across the inductor? That has to be 0 if it is steady state. Both the inductors average voltage has to be 0. So, what is left is what is being written here, Vn minus VL1 minus Vc1 minus VL2 minus V0 is equal to 0. So, this average is 0, this average is also 0. So, what is remaining is that your capacitor voltage 1 would be the difference between input voltage and the output voltage. So, Vc1 will be Vin minus V0. Remember, V0 can be less than Vin, it can be equal to Vin, or it can be even more than Vin. So, the capacitor can have positive or negative polarity. We cannot say that until we know the output voltage. Remember this result. Okay. Now our analysis begins now with the switch closed. Okay, the switch is closed between 0 to dTs. Ts is the switching period, of which a portion of that, where d is less than 1, the switch is closed. Now, when the switch is closed, the diode D will be open circuited. Okay. Now, let us see the analysis. Now, see the input, now C1 is a part of output circuit. C1 is a part of output circuit. This circuit, C1 is connected to the output portion or the load portion. Okay, let me write it load itself. C1 is a part of the load circuit, not the source circuit. When diode is conducting, then C1 will be a part of the source circuit. We will discuss it shortly. Now, in this configuration where the switch is closed, what is the capacitor current? Remember, we are using Ampere-second balance for Cuk converter analysis. So, we are not bothered about volt-second balance. We will do that little later, but for deriving the voltage gain, we will be focusing on Ampere-second balance. Okay. So, I am interested in finding the value of IC1 when the switch is closed. So, what is IC1? See this branch, IC1, IL2, they are numerically same, and they have, since they are flowing in opposite directions, IC1 will be equal to minus IL2 when the switch is closed. So, we have found out the current flow through the capacitor when the switch is closed, and we found that it is equal to minus IL2. Okay. Now, next analysis is based on when the switch is open, that is until DTS switch was closed, then we remove the pulse to the MOSFET or IGBT. Now, the switch is open and it will remain open for the rest of the time, that is from DTS to TS or 1 minus DTS. The duration is 1 minus D times TS. For that much time, the switch will become open. For that much time, the diode will also become closed. Now, see, the capacitor which was earlier the part of the load now is part of the source circuit, See, the capacitor is connected with the source. Earlier it was part of the load, now it is part of the source. Now, capacitor gets charged from the source, and once the switch is closed, the stored charge in the capacitor will be used to feed the load. So, that is why I said capacitor is the element which takes part in power transfer along with inductors, definitely along with inductors, but in earlier 3 circuits what you have learned, the capacitor was just a filter, the inductor was playing the role of power transfer. Here it is the capacitor which is doing along with inductors. Okay. Now, the capacitor, when the diode is closed or when the switch is open, the capacitor C1 becomes the part of, remember this is C1 becomes a part of source circuit. Now let's find out what is the value of IC1. You see, IL1 and IC1 is in series path, so they has to be numerically same. The direction of both of them are also same. So, IC1 will be equal to IL1 when the switch is open. When the switch was closed, IC1 was equal to minus IL2. Okay, which means the capacitor has only 2 values. When the switch is closed, it is equal to minus IL2. When switch is open, it is equal to plus IL1. That is, the capacitor voltage is either inductor current 1 or inductor current 2. Okay. Now, we have found out the current flow through the capacitor in either switch topologies. Now, let us do the analysis part. Now, this will be the shape of the capacitor current. Okay. See, when the switch is now 0 to dTs, the switch is closed, and then when dTs to Ts, it is open. It is closed again, it is open, switch is open again. So, when it is closed, the current through the capacitor is minus IL2, minus IL2. When it is open, current through the capacitor is plus IL1, and this cycle repeats. If you see the net average, this area and this area, if it is A1 and if it is A2, this area is A2, A1 will be equal to A2 if the circuit has attained steady state. And our assumption is that we are operating in a circuit which is in steady state. So, hence A1 will be equal to A2. So, that precisely is the Ampere-second balance here. Earlier we were using volt-second balance, but here the y-axis is Ampere, the capacitor current, and x-axis is time in seconds. So, that is why Ampere into second, which is the area under the curve, they has to be same. So, IC closed is minus IL2 and IC open is plus IL1. Now, now let us try to derive the voltage gain of the Cuk converter. The components are ideal, which is the fifth assumption what we made. So, input power is equal to output power, there is no losses. This is just an assumption. In reality, there will be some amount of losses. So, V in IN, input voltage into input current is equal to output voltage into output current. The average input current is same as the average current through IL1. Let us see why is it so. See the topology. IL1 and IN, the source current, are they not the same? Always when the switch is closed, it is so. When switch is open, even then IL1 is same as IN. Thus, we can say your input current is same as average inductor current. And how about IL2? The average IL2 will have steady state and ripple will flow through the capacitor and steady state will flow through the inductor. So, the average IL2, which is the steady state part, is equal to I0. See, the switch is open. Now, IL2 is same as the output current, average output current. When switch is closed, even then, see, the configuration is inductor, that current splits into capacitor and resistor. So, the steady state portion of this one flows through the load and the ripple portion will flow through the capacitor. Even that is true even when the switch is closed or the switch is open, irrespective of the topology or the configuration of the switch. I0 is equal to IL2, and irrespective of the topology of the switch or the configuration of the switch, input current is equal to IL1. This is an important result as far as Cuk converter is concerned. That is, switch is closed or open, input voltage is in series with the input filter inductor L1. So, IN is equal to IL1. These both are same. Similarly, irrespective of the switch is closed or open, IL2 is connected in parallel with the C2 and R, where C2 accepts the ripple and steady state portions, or the average IL2 will flow through the load as load current. That happens when the switch is closed or switch is open. Okay. So, I0 is IL2. That is what is being written here, and I have made a mistake. This is not IN, this is IO. Output current IO is equal to IL2. Okay. Now, using Ampere-second balance, IC1 closed into the duration for which the switch is closed, which is dTs, plus IC2, this is IC1 itself, I am sorry, IC1 open into the duration for which the switch is open, which is 1 minus d into Ts is equal to 0. So, what is IC1 closed? When the switch is closed, the current through the capacitor is minus IL2. So, minus IL2 dTs plus the capacitor current when the switch is open is plus IL1. So, IL1 into 1 minus dTs. You add them up and equate it to 0, you will get IL1 by IL2 is equal to d by 1 minus d. But what is IL1? Average load current, average inductor current 1, we have just now seen that it is equal to input current itself. And what is IL2? We have seen it is equal to the average output current. So, that is what is being written here. IL1 is same as IN and IL2 is same as I0. So, the current gain we have derived it, current gain of the Cuk converter we have derived. This is the expression. But we are more interested in finding the voltage gain. So, that is pretty easy. Vin into In is equal to V0 into I0. This is based on the assumption number 5 where the components are ideal. So, the efficiency is 100%. There is no losses. Now, what is In? It is nothing but IL1. What is I0? It is nothing but IL2 minus IL2. Okay. So, you divide, take the gain V0 by Vin is equal to minus IL1 by IL2. IL1 by IL2 we have d by 1 minus d. So, minus IL1 by IL2 will become minus d by 1 minus d, and this minus sign is responsible for the polarity reversal at the output. This it is interesting to see that the gain of the Cuk converter is exactly same as the gain of a buck boost converter. Okay. So, it can operate at a voltage lesser than the input if the duty ratio is less than 0.5, and if the duty ratio is more than 0.5, the output voltage will be more than the input voltage. Then in that case it will work as a boost converter. But unlike a buck or a boost, the output will have a polarity reversal. That is why this negative sign has come. So, we have just now derived the voltage gain of the Cuk converter. Now, we have found out the voltage gain of the Cuk converter. Now, let us do the output filter capacitor design. Okay. See, if you see observe the circuit diagram, yeah, this L in series with the parallel combination of C and R. This is the, I think at least some of you would have got an idea, this is the output stage of a normal buck converter. Okay. In this kind of a output stage you have seen in buck converter. So, there is no difference. We can, instead of doing this extensive analysis, we can straight away use the output voltage ripple equation of buck converter. That is the output capacitor C2, the inductor L2 and the load R in the same configuration as a buck converter. Okay. So, inductor current also has the same form as the buck converter, that is the voltage current rises, then it falls. Okay. Therefore, the ripple or the variation in the output voltage is same as for the buck converter. So, for a Cuk converter as well as for a buck converter, the output voltage ripple is given by the formula 1 minus d by 8 L2 C2 F square. In buck converter it was only LC because there was no L1 or L2, there was only a single inductor and there was a single capacitor, but here it is L2 C2, second inductor and the second capacitor, and F square, switching frequency square. Numerically, this is the expression for the output voltage ripple expressed in percentage. Into 100 you will get percentage. So, once this is specified by the user, the allowable output voltage ripple is specified, which will be usually less than 1%, then we can derive the value of C2 if we know the value of L2. Okay. So, this is how the filter output capacitor filter is selected, but to do that we need to know the value of L2. Now, our task is to find out L2. Similarly, L1 also is needed. Now, let us get into that. Now, when the switch is closed, what is the current variation? That is what we are going to see. Now, I have written in two columns the current variation in L1 and L2. This is when the switch is closed. So, let us take the circuit. This is the configuration when the switch is closed. What is the inductor voltage 1 when the switch is closed? If you have a doubt, write the Kirchhoff's voltage law for this mesh. What is it? Vin minus VL1 must be equal to 0, or VL1 is equal to V input. This is the inductor voltage 1 when the switch is closed. Now, that is what is being written here. The inductor voltage 1 is equal to input voltage itself, and VL1 is nothing but L1 dIL1 by dt as per Faraday's law. Now, what happens is that you can take L1 to the denominator. So, Vin by L1 is equal to dIL by dt. Now, input voltage is a constant, L1 is the value of the inductor which is also a constant. So, this ratio becomes a constant. So, when the rate of change of current is constant, current rises linearly or falls linearly if this term is negative. So, but the variation is linear. So, we can write delta IL1, that is the change in current when the switch is closed, by dt, the duration for which the switch is closed, which is d times Ts, duty ratio times Ts, switching cycle, is equal to Vn by dTs. If you cross multiply dTs there, you will get delta IL1 closed is equal to Vn dTs by L1. So, this result we will be using it. Now, we have found out the current variation in inductor L1 when the switch is closed. Now, let us do the same thing for L2. So, let us start by writing the switch is closed, write the Kirchhoff's voltage law across this loop. Okay, the polarity must be like this. I am sorry for that, because see, the current is entering the positive terminal. I am sorry for this mistake. So, plus is here, minus is here. So, this becomes minus Vc1 plus Vl2 minus V0 is equal to 0. I am really sorry, because the current is flowing into this one, into the inductor like this. Since I have chosen the current direction to be like this has to be the positive terminal of the inductor voltage VL2. So, the equation becomes minus Vc1 plus VL2 minus V0 is equal to 0. Take VL2 outside, you will get it is V0, take this V0 out there, it becomes plus V0, and minus Vc1 when it goes to the RHS, it becomes plus Vc1. And what is Vc1? We have already derived. If you remember, the first step we did was that. See, Vc1 is nothing but input voltage minus output voltage. So, Vc1 is input voltage minus output voltage. So, this minus V0 and this V0 will get cancelled. So, there also you will get the voltage across the inductor is same as the input voltage, exactly as in case of VL1. So, VL2 is also equal to Vn, which is equal to L2 dIL2 by dt. Same analysis, delta IL2, that is the change in current L2 when the switch is closed, is given by Vn. What is the duration for which the switch is closed? It is dTs. So, this dt, once it becomes into the numerator on the LHS, it becomes dTs by L2. Okay. So, the change in current is Vn dTs by L2. They both of them will be linearly increasing, but with different slope, because this is L1 and this is L2. If they are same, then they will be exactly similar, but since L1 and L2 most probably will be different, they will be linearly rising, but with different slopes. Okay. Now, this is the variation in inductor current when the switch is closed. This is the average inductor current. Let it be IL1 or IL2. Either way it is okay. This is the shape. Okay. And this is IL minimum value. This is a value. So, let it be capital letter. And this is IL maximum. And what is the ripple? This would be the ripple. That is IL maximum minus IL minimum would be the ripple current. Average would be this much. So, what is this? This would be delta IL by 2. And what is this much? This is also delta IL by 2. So, that is why in previous lectures we have written IL max is equal to average inductor current plus delta IL by 2. IL minimum is equal to average inductor current minus delta IL by 2. So, the same thing we are going to use here. I have just explained what is critical inductance, which you already know, because last three converters we have discussed it in detail. What is the criteria for the circuit to be operating in continuous conduction mode? That is, IL min should be greater than or equal to 0. What is IL min? The average inductor current minus delta IL by 2, which is the IL minimum, should be greater than or equal to 0. When it is equal to 0, it becomes the boundary condition between continuous conduction and discontinuous conduction mode. So, it should be greater than or equal to 0. You take this one to the right side. So, you will get the condition for continuous conduction is that IL should be greater than delta IL by 2. That is, the average inductor current must be more than 50% of the ripple. That is once this condition is satisfied, you can be dead sure that the circuit is operating in continuous conduction mode. So, that is what we are going to do now. The boundary condition becomes IL1 should be greater than 0.5 delta IL1. Similarly, IL2 should be greater than 0.5 delta IL2. This is the boundary condition. And what is IL1? We have just now found out. See the ripple current. So, IL1, this Ts on the numerator becomes 1 by Fs, that is it becomes switching frequency in the denominator. So, V in d Ts by L1 becomes V in d by L1 Fs. Half this 0.5 becomes 1 by 2, that is why this 2 appears here, that is equal to In. This we have already seen. Input current is same as the inductor current. Similarly, output current is same as the IL2. So, that this result we have already seen. So, we have written IL1 is equal to this is the boundary condition. At the boundary condition, IL1 is equal to V in d by 2 L1 Fs into In. If it is operating in the boundary condition, what is L1? It becomes L1 critical. Not just any value of L1, it is the critical value of the inductance L1, because this formula is valid at the boundary condition. So, L1 critical, take L1 outside, bring IL1 downside, it becomes V in into d by 2 IL1 Fs or I in Fs, because IL1 and I in are same. Now, what is V in? It is nothing but V0 into 1 minus d by d. This is based on the voltage gain equation of the Cuk converter. This d by 2 Fs is there, d by 2 Fs is there. Then what is I in? Use the current gain. Okay, I0 into d by 1 minus d, that 1 minus d goes into the in the numerator. Now, what all things you can do here is that this d and this d gets cancelled. 1 minus d and 1 minus d becomes 1 minus d square. V0 is there in the numerator, 2 Fs is there in the denominator, and I0 d is also there. Now, see, V0 is there in the numerator, I0 is there in the denominator. What is V0 by I0? Output voltage by output current, that is nothing but the load resistance R. So, this V0 by I0 becomes R into 1 minus d square by 2 dFs. So, V0 by I0 is R 1 minus d square as it is by 2 Fs into d. So, 2 dFs. So, this is the critical inductance of inductor 1. If you calculate this value and take as a thumb rule, we take 25% extra, then you can be sure that the current through IL1 will be operating in continuous conduction mode. Similarly, we have to do the same analysis for inductor 2 as well. Okay, that is what we are going to do now. IL2 should be greater than or equal to at the boundary condition. Remember, so it should be greater than or equal to, at the boundary it is equal to 0.5 times the ripple in IL2. So, IL2, which is the average output current itself, is equal to 0.5 IL2. This equal to is because of the boundary condition. At the boundary condition, they are equal. Above, if it is in CCM, it should be greater than. But since we are trying to find out the critical inductance, we take the boundary condition, which is equal to. And what is delta IL2? We have found out it is V in dTs by 2L2. This 0.5 becomes 2 in the denominator, 1 by 2. And what is this? At the boundary condition, this is not just a L2, this is L2 critical. Take it there. So, L2 critical is V in d Ts by 2 I0. Okay. So, it becomes V0 into 1 minus d by d into d by 2 I0 Fs. How did we do that? This Ts becomes 1 by Fs, it goes into the denominator, and this I0 comes into the denominator, 2 is already there, and V in you convert it into V0 using the voltage gain of the Cuk converter, which is d by 1 minus d. So, that is what we have done here. Now, this d and this d gets cancelled, we will get, there is a V0 here, there is an I0 here, so it becomes R here. So, R into 1 minus d in the numerator and 2 in Fs in the denominator. So, R into 1 minus d by 2 Fs. This is the critical inductance of the second inductor. If you choose 25% or anything more than this critical value, the circuit will operate in continuous conduction. If L1 and L2 are chosen to be above their critical inductance value, then the current through them will be in continuous conduction, which means the circuit will be operating in continuous conduction mode. So, this is how you design the values of L1 and L2. C2 we have already found out. How do we design C2? That is based on the specification by the user, that is how much is the permissible voltage ripple in the output voltage. With that we can decide C2, and L1 and L2 we have decided based on what is their critical inductance. Now, one thing is pending, which is the design of capacitor C1. That is a very critical part, because that is an integral element which takes part in the power transfer process. So, we have to find out the ripple on C1. When there is a current flow through C1, voltage will fall or rise depending on the direction of current, and that will contribute to some ripple. So let's see that the ripple in C1 can be estimated. Now the trouble is that I will come to it shortly. The ripple in C1 can be estimated by computing the change in VC1. In the either there are two intervals when switch is closed or switch is open. We will consider switch is open. If you are comfortable with switch is closed, you can do that as well. Here IL1 and IC1 are same. That is, when the switch is open, IL1 is equal to IC1. Remember, IL1 has a pattern like this, and I will like this. It either rising linearly or falling linearly. But with such a current pattern, it will be difficult to do the integration. So what we do is that we assume the current IL1 to be constant. This is not a 100% accurate estimation, but still we are using this one for the sake of simplicity of the calculation. So that's why I have written delta VC1, change in voltage across the capacitor is not equal to, it is approximated to be 1 by C1 integral from, since I am considering open, the time is from DTS to TS, and IL1, which is same as the capacitor current, IC1 into dt. So once you take IL1, which is taken to be a constant, which is approximated to be a constant, you can take it outside of the integration. So it becomes IL1 by C1, and once you integrate over the limits dt, you will get 1 minus d into Ts. So IL1 by C1 into 1 minus d into Ts. See, this is based on the assumption that IL1 is constant. In reality, it is not so, but for the sake of doing simplifying the calculations, we are taking this assumption. So what is delta C1? It becomes this one, IL1. What is IL1? IL1 is nothing but the input current itself. Input current itself. Let me draw it here. We have found out delta VC1 is approximated to be IL1 by C1 into 1 minus d Ts. So this can be approximated to be, let 1 minus dTs be there as it is, C1 is also there. What is IL1? That is what we are going to see. IL1 is nothing but I input. Okay. So we are interested in expressing it in output voltage terms. If that is the case, you convert it to I0 using the transformation ratio, T by 1 minus d into I0. This is I0 is same as IL2. Okay. So what happens is that this becomes, this 1 minus d and 1 minus d gets cancelled. What you are left is d IL2 Ts by C1. What is IL2? This is nothing but I0 itself. So what you get is that, how can we write I0? V0 by R. So it is dV0 by R. C1 is already there. This Ts from the numerator becomes 1 by Fs. So dV0 by RC1 Fs. That is what is being shown here. The output voltage ripple is approximated to be V0 into d by RC1 into Fs. If you want, you can express it in V in terms also. That is also possible. But then the equation becomes more complex and 1 minus d terms will come. So that's why I have chosen to be V0. That's why some steps are there in between. If you are comfortable expressing in terms of input voltage, you are free to do that. Only thing, this expression becomes slightly more complex, but numerically you will get the same answer. So I will explain once again. Change in ripple is taken to be 1 by C integral IC dt. IC1 is same as IL1, and when the switch is open, the limits of integration is from dTs to Ts. So you will get IL1 by C1 1 minus dTs, but IL1 is same as I input. So you convert either to input voltage or output voltage. For that I have used current gain of the Cuk converter, and once you do that, you get I0 in the numerator. This I0 can be converted into V0 by using the formula Ohm's law. So you get V0 here in the numerator, and denominator you get R. V0 by R is the I0 itself. So that's how delta V1 is expressed in terms of the output voltage with this formula. Okay. So, we have found out the ripple in the capacitor C1. Most probably in the design specification, the user would specify how much is the allowable ripple across the capacitor C1. Once that is known and once the output voltage is defined, then we can find out the value of capacitance C1. Because duty ratio is dependent on the output voltage, P0 is again the user specification, switching frequency is what we have chosen, load resistance is what the user has given. Now, if he specifies what should be the allowable voltage ripple, then we can easily find out C1, because that is the only unknown in this equation. Remember, this is not exact, this is approximated. And why this approximation? Because we have assumed IL1 to be constant, whereas it is not constant, it will be rising and falling. Since we are considered switch is open, the current will be falling. But for sake of simplicity, we have assumed this IL to be constant. This error we purposefully make with the intention of making the calculation simpler. We sacrifice accuracy for simplicity. Hope you have understood this. So, to summarize, Cuk converter is a fourth order converter. Why fourth order? Because there are 4 storage elements, 2 inductors and 2 capacitors. The capacitor, not all capacitor C1 takes part in power transfer along with the inductors. This is a peculiarity of Cuk converter compared to the other 3 converters we have learned earlier. The capacitor C1 is connected to the input circuit when the switch is opened and is connected to the output circuit when the switch is closed, which means sometime it is connected to the source where it gets charged, and once some remaining portion of the circuit of the switching cycle, it is connected to the load wherein the charge is given to the load. So, the capacitor is charged, then capacitor is discharged, capacitor is charged, capacitor is discharged again. Thus, this cycle repeats. That is why I said capacitor takes part in the power transfer process along with the inductors. Now, L1, which is connected in series with the battery or the source, acts as an input current filter, and it prevents harmonic conduct at the source. Okay, and designer has to ensure that both inductor L1 and L2 are above their critical inductance, so that the circuit operates in continuous conduction mode. How do we do that? We have to calculate L1 critical, L2 critical, take 25% extra. 25 is just a thumb rule, you can take anything above that. 25 is a reasonably good bet, so that both of them will be operating in continuous conduction mode. Okay, and the flip side is that the output has a polarity reversal, which is similar to the buck boost converter. That is, the input voltage is plus 12, output will have a minus polarity at the terminal, and the output can be higher or lower, similar to a buck boost. They are much more versatile than a buck converter or a boost converter acting alone. So, this concludes the discussion on Cuk converter. To make it familiar, we will do a new design numerical so that the design of Cuk converter becomes familiar to you. So, this is an example. You are asked to design a Cuk converter to generate an output voltage of 18 volt from a 12 volt source. That is, your required output voltage is 18 and 12 is the input battery. Okay, the load power is 40 watts. Okay, the power of the load is given as 40 watts. You are asked to choose the duty ratio D, switching frequency Fs. You are asked to find out L1 and L2, and what is the specification? Delta IL should be limited to 10%, and delta V0 should be less than 1%, and voltage ripple in C1 should be less than 5%. So, these are the design constraints. With these design constraints, let us design a Cuk converter which can develop an 18 volt output from a 12 volt to feed a 40 watt load. The first step to do is to find out the duty ratio. So, output voltage by input voltage is equal to minus D by 1 minus D. So, this 18 volt is actually minus 18 volt. So, you get minus 18 by 12 is equal to D by 1 minus D, okay, or 1.5 into 1 minus D is equal to D. 2.5 D, or D becomes 0.6. This is an answer. The duty ratio is 60%. So, we have found out the duty ratio. Switching frequency, you can choose any frequency, preferably above 20 kilohertz. I am using 50 kilohertz. So there is no unique answer. As a designer, you are free to choose any frequency you want. Okay, even if someone chooses 100 kilohertz, it's still fine. Only thing is that you have to develop a 100 kilohertz pulse triggering circuit. Okay, so I am choosing 50 kilohertz. So remember, there is no unique answer for this. Depending on the frequency chosen, your all other values will change. So I have chosen frequency to be 50 kilohertz. Now let's design the real components. So what is the output current, which is the average inductor current 2? It's nothing but P0. Output power, which is 40 by V0, which is 18 volt. This comes to be 2.22 ampere. So this is the average inductor current 2. Similarly, what is the source current, which is the average inductor current, which is, since we are assuming ideal components, P0 will be equal to Pn. So 40 by input voltage, which is 12 volt. 40 by 12, you will get 3.33 ampere. So this is the average current through inductor L1. Now what is delta IL1? Now delta IL is nothing but V in dTs. V in dTs, Ts I will take it as Fs in the denominator into L. This is the general expression for ripple. This is true for L1 as well as L2. Now how can we design L2? Let's design first L2. L2 should be greater than or equal to V in into D by Fs delta IL. Delta IL2. Since I am designing L2, this is delta IL2. Okay, what is delta IL2? We are given a constraint that the current ripple should be 10%. 10% of what? 10% of IL2. And what is IL2? See, IL2 is 2.22 ampere. So this is 0.222 ampere. 2.22 ampere is IL2. 10% of that is 0.222 ampere. So what is L? How can you calculate L2? L2 happens to be, L2 should be greater than or equal to, what is input voltage? 12 volt. What is duty ratio? 0.6. Switching frequency is 50 kilohertz. Delta IL2 is 0.222. So this comes to be 649 something you will get. Since it should be greater than or equal to, I am giving 650 microhenry. So this is a answer. 650 microhenry L2 will ensure that the output voltage ripple, the ripple current through L2 will be less than this much, 10%. Same analysis you can do. How will you calculate L1? It is nothing but V into D by Fs into delta IL1. IL1 is 3.33. So delta IL1 is 3.333 ampere. So let's do that. L1 should be greater than or equal to V in D by Fs delta IL1. It is greater than or equal to 12 into 0.6. Fs is 50 kilohertz into, what is delta IL1? 3.33 is IL1, 10% of that one is 0.333. So your IL1 you will get, L1 you will get it as 433 something. So I am approximated to be 435 microhenry. So that your ripple will be less than 10%. So we have designed L1 435 microhenry, L2 650 microhenry. Okay, now what is left is we have to design C1 and C2. For that, delta this output voltage ripple is 1 minus D by 8 LC Fs square. This is the same as that of a buck converter, but unlike a buck we have L2 and C2 here. So that's it. 1 minus D is 0.4. 8. What is L2? L2, what is it? We got 650 microhenry. C2 is what we have to find out, into switching frequency is 50 into 10 raised to 3 square. And what is this? This is the ripple. And what is the constraint? Remember, output voltage should be less than 1% or 0.01. If you solve C2, because everything is known, only C2 is the unknown, you will get C2 to be equal to 3.082 microfarad. So, if it is exactly 3.082, then the ripple will be 1%. So, choose C2 to be approximately, say, next standard value, let it be 4 microfarad if it is available, or the next standard value is guarantees that the output voltage ripple will be less than 1%. Now, C2 has been designed. Now, only thing pending is C1, which has to be designed, for which they have specified the allowable voltage ripple across C1 is 5%. So, using the same analysis, C1, we have derived this formula as the last step, dV0 by R Fs delta Vc1. Now, it is important to find, remember, delta Vc1, it is not percentage, it is absolute value of the ripple voltage. So, we have to find out Vc1. What is Vc1? It is nothing but the input voltage minus output voltage. So, input is 12 minus output is 8 minus 18. So, the capacitor voltage is 30. So, they are allowing 5% of it. So, delta Vc1 is equal to 5% of 30 volt. So, allowable ripple is 1.5 volt. So, that is what we are going to use. D is 0.6, output voltage is 18. R is, what is the load resistance? We know output voltage is 18, output current is 2.22. So, V0 by I0 will be the load resistance, that is what we given here. 50 kilohertz is the switching frequency, delta Vc1 is 1.5 volt. Let me, since shortage of space is there, if you calculate it, this will be equal to up 17.8 microfarad. So, choose a value higher than this, maybe 18 or 20 microfarad, then you can guarantee that the voltage will never exceed 1.5 volt. The ripple voltage will never exceed 1.5 volt. So, we have designed C1, which is 18 microfarad, we have designed C2, which is 4 microfarad, we have designed L1, which is L1, where is it? Yeah, L1, which is 435 microhenry. We have designed L2, which is 650 microhenry. We have calculated the duty ratio, which is equal to 0.6, and we have chosen a switching frequency of 50 kilohertz. If we do all this, we can guarantee that all these constraints are met, and simultaneously we will attain a 18 volt output from a 12 volt battery to feed a power to a 40 watt resistive load. And this is how we do the design of a Cuk converter. I hope the working of the circuit, the methodology adopted for the calculation of voltage gain, how we have calculated the critical values of inductance and how we have designed the capacitors. Hope everything is clear to you. Thank you.